In this lecture we find out the area of pentagon ABCDE. In the drawing we have pentagon ABCD. In the drawing we have pentagon ABCDE. Side ED of this pentagon ABCDE is equal to 1 unit sinister. Side EC also equals to 1 unit sinister. Side AB equals to 1 minus x unit sinister. Side CB equals to 1 unit sinister. Side DC equals to x. Again, our task is to find out the area of this pentagon ABCDE. So first of all, we'll join points E and C together by straight line. And we'll join points E and B together by straight line. In the next step, we will extend side BA by straight line in such a way that the extended part will be equal to x units in this time. We define this point as point M. So actually extended side VA in such a way that AM will be equal to x according to our construction. So it again AM equals to x according to our construction. When you extend a straight line by straight line, the result is a straight line. So we extended the straight line BA by straight line, the result BM is also a straight line. So here we know that the sum of, according to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of BM at point A? We have this angle that is right angle plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees and its size. Repeat again that AM equals to x according to our construction. AM equals to x according to our construction. In the next step, we join points E and together by straight line. By joining points E and M, we create the right triangle EMA. So, in the next step, we prove that the right triangle EMA, this right triangle EMA is congruent to this right triangle CDE according to side angle side rule. So, I copy those two right triangles in a new page, and we prove that those two right triangles can go into each other. This is the right triangle EMA. This is the right triangle CDE. Actually, those are the two right triangles that are coming from the original drawing. This is right triangle EAM and this is right triangle CDE. So what those two right triangles congruent to each other? First of all, side AM on the right triangle EMA on the right triangle EAM is equal to side CD of this right triangle EDC. And again, side AM equals to side CD. They are both equal to x and therefore they are equal to each other. In addition, side EA of the right triangle AME is equal to side ED of the right triangle CDE. They are both equal to 1 and therefore they are equal to each other. So okay, now side AE is equal to side ED equals to 1. And angle EAM on the right triangle EAM is equal to angle EDC on this right triangle EDC. They are both right angles and therefore they are equal to each other. So angle EAM in the right triangle EAM is equal to angle EDC. In the right triangle EDC, they are both equal to 90 degrees and therefore they are equal to each other. So I can prove that those two right triangles congruent to each other according to side angle side rule. Again, those two sides and the angle that is included in both those two sides and the angle that is included between those two sides in the right triangle ECD are correspondingly equal to those two sides and the angle that is included between those two sides in the right triangle EMA. And therefore those two right triangles congruent to each other according to side angle side rule. So if you know, we follow that the right triangle CDE congruent, this is the same congruent to the right triangle EAM according to side angle side rule. And from the fact that those two right triangles congruent to each other, we will derive that side EM equals to side EC. According to the rule that corresponding sides of congruent triangles are equal to each other. Those two triangles congruent to each other, and therefore the two corresponding sides EM and EC must be also equal to each other in the reverse. So side EM equals to side EC. Side EM equals to side EC. In addition, from the fact that those two right triangles congruent to each other, we will derive that they are also the same areas. That is to say, the area of the right triangle EAM is equal to the area of this right triangle ECD. So, if you know, if you find out that the area of the right triangle ECD is equal to the area of the right triangle EAM. So the area of this right triangle EAM is equal to the area of this right triangle EDC. This is right triangle EAM, and the area of this right triangle EAM is equal to the area of this right triangle EDC. We define the size of the area of this right triangle as Z, that is to say it is equal to Z squared in its size, and from this equation Z equals to the area triangle EAM equals to the right triangle ECD, and we have that the right triangle ECD also equals to Z squared in its size. In the next step, we prove that triangle EMEE, triangle MEB, this is triangle MEB, conjoined to this triangle EBC. But first of all, what is the length of side MB? The length of side MB in total equals to x plus 1 minus x. Again, MB in total equals to MA plus AB. That is to say, MB equals to x plus 1 minus x. So now we should find out that MB in total equals to MA plus AB. So MB equals to MA, that is x, plus AB, that is 1 minus x. So MB in total equals to x plus 1 minus x. We have x minus x is 0, and we left only with 1. So in total found out that MB equals to 1 unit in its length. This is side MB, that is equals to 1 unit in its length. So the next step, we prove that triangle MEB conjoined to this triangle EBC. Triangle EMB conjoined to this triangle EBC. So I'll copy those two triangles in the new page, and we prove that they can point to each other according to side rule. So why those two triangles can go into each other? First of all, we already found out that those two sides are equal to each other. That is to say, side EM, this triangle EM, this triangle EMB is equal to side BC, to side AC of this triangle EBC. So if you found out that EM equals to EC. In addition, side MB on this triangle EMB is equal to side CB on this right triangle ECB. They are both equal to 1 and therefore they are equal to each other. MB equals to BC equals to 1. And finally, EB is a common side that belongs to both triangles. So we can write down that EB equals to itself is a common side that belongs to both triangles. So we found out that all the three sides of this triangle EMB are correspondingly equal to all the three sides of this right triangle EBC, and therefore those two right triangles can go into each other according to side, rule. So let's go on. Again, if we found out that triangle EBC congruent, this is the side of congruent to triangle EBM according to side rule. And from the fact that those two right triangles congruent to each other, we derive that they are also the same areas. That is to say, the area of triangle EBM is equal to the area of this triangle EBC. So if we found out that the area of triangle EBM is equal to the area of this triangle EBC. Again, if you follow that the area of triangle EBM is equal to the area of triangle EBC because they can go into each other. In the next step, we calculate the area of this triangle EBM. So, what is the area of triangle EBM? The area of this triangle EBM equals to the base MB times the height AE over 2. And again, the area of the triangle EBM total equals to the base MB times the height AE over 2. MB is 1, AE is also 1, divided by 2. So in total, if you know that the area of this triangle EMB is equal to 1 times 1 is 1 over 2. Then triangle EBM equals to 1 over 2 squares in its size. So we can write here that the area of triangle EBM equals to 1 over 2 squared in size, and for this equation 1 half equals to the area of triangle EBM equals to the area of triangle EBC. We derive that the area of triangle EBC must be also equal to 1 over 2 units in its length. So the area of triangle EBM equals to the area of triangle EBC. Each of them is equal to 1 half. And therefore, the area of triangle EBM plus the area of this triangle EBC will be equal to 1 half plus 1 half. That is 1 half plus 1 half is 1. So in total, the area of this triangle EBM plus the area of this triangle ECB is equal to 1 half. So, what is the area of quadrilateral EBMC? This is quadrilateral EMBC. The area of this quadrilateral EMBC is equal to the area of triangle EBM plus the area of this triangle EBC. And again, the area of this quadrilateral EMBC in total is equal to the area of triangle EBM plus the area of triangle EBC. We already found out that the area of this triangle EBM is 1 half, and the area of this triangle EBC is also 1 half. So in total, the area of the big quadrilateral EMBC will be equal to 1 half plus 1 half, that is 1. So in total, we found out that the area of the big quadrilateral EMBC is equal to 1 square in its size. We know that the area of this quadrilateral EMBC is also equal to the area of this triangle EMB, is equal to this square in its size, plus the area of this quadrilateral EMBC. So write it down. And again, the area of this big quadrilateral EMBC in total is equal to the area of the green triangle EMA plus the area of this quadrilateral EMBC. So write it down. The area of the big quadrilateral EMBC in total it is equal to the area of the green triangle EAM plus the area of this quadrilateral EABC. This is quadrilateral EABC. And again, if you found out that the area of the big quadrilateral EMBC in total it is equal to the area of the right green triangle EAM plus the area of quadrilateral EMBC. And we know, we already found out that the area of the big quadrilateral EMBC is equal to 1. So you can find out that in total the area of the quadrilateral EMBC is equal to 1. So the area of this big quadrilateral EMBC will be equal to the area of the great quadrilateral EM8 is equal to Z plus the area of this quadrilateral EABC. And we already found out that the area of the big quadrilateral EMBC is equal to 1. So we found out that the area of the big quadrilateral EMBC is equal to Z, that is the area of the right hand triangle, plus the area of quadrilateral EABC. So from this equation, we derive that Z plus the area of quadrilateral EABC is equal to 1. Again, Z plus the area of quadrilateral EABC in total it is equal to 1. So if you know that the area Z plus the area of quadrilateral EABC is equal to 1. And again, if you found out that Z plus the area of quadrilateral EABC is equal to 1. Our task is to find out the area of pentagon ABCD. This is pentagon ABCD. Again, this is pentagon ABCDE. So what is the area of this pentagon ABCDE? The area of pentagon ABCDE in total is equal to the area of this pentagon ABCD. In total it is equal to the area of the great quadrilateral EDC plus the area of this quadrilateral EABC. And again, the area of the big pentagon ABCDE equal to the area of the great quadrilateral EDC plus the area of quadrilateral EABC. So we only found out that the area of this quadrilateral EDC is equal to Z. So it's also the area EDC by Z plus the area of this quadrilateral EABC. So in total, we have found out that the area of pentagon ABCD is equal to Z plus the area of quadrilateral ABCE. So here the area of pentagon ABCD equals to Z plus the area of quadrilateral ABCDE, the area of quadrilateral EABC. But we already found out that Z plus the area of quadrangle AEBC is equal to 1. So we can write here that Z plus the area of quadrangle EABC equals to 1. Z plus the area of quadrangle EABC equals to 1. So in total, we have found out that the area of pentagon ABCD is equal to 1. So as you know, and that is the answer to our question. Actually, what is a pentagon? A pentagon is a shape that has 5 sides that or 5 lines, 5 sides. So this is a pentagon ABCD. It has 5 sides. So the answer to the question is that the area of this quadrangle the area of this pentagon ABCD is equal to 1 square units in its size. So in the next step, I'll start the lecture. Repeat again on the definition of a pentagon. A pentagon is a plane figure with 5 straight sides and 5 angles. Actually, this is pentagon ABCDE. You can see that it is a plane figure with 5 sides, 1, 2, 3, 4, 5, and 5 angles. 1, 2, 3, 4, 5. Okay. So our task in this question was to find out this pentagon ABCDE. So in the moment we have pentagon ABCDE. Side ED equals to 1 unit in its length. Side EA also equals to 1 unit in its length. AB equals to 1 over x. BC equals to actually side ED equals to X units in there, side DC equals to side ED equals to 1 unit inside, side DC equals to X, side CB equals to 1. This is a right angle, and this is also a right angle. Again, our task is to find out this pentagon, ABCD. So in the first step, we join points E and B together by a straight line, and we join points C and C together by a straight line. Then we extended side BA of this pentagon ABCDE by a straight line in such a way that the extended part, this is the extended part AM, will be equal to X units in its length. So AM equals to X according to our construction. And again, AM equals to X according to our construction. When we extend a straight line by a straight line, the result is a straight line. So we extend the straight line VA by a straight line, and the result is BM. So BM must be also a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? Here we have this angle is a right angle according to what is in the question. So plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we prove that those two right angles can go into each other according to side angle side rule. So when those two right angles can go into each other. First of all, side DC of this right angle EDC is equal to side AM of this right angle EAM. They're both equal to X, and therefore they're equal to each other. In addition, side DE of this right angle EDC is equal to side EA of this right angle EAM. Therefore equal to 1, and therefore they're equal to each other. And this is again EDC, this is right angle, and it is equal to this angle EAM, this is also right angle. So if you prove that those two right angles can go into each other according to side angle side rule. That is to say, those two sides and the angle that is included between those two sides is right angle EAM, are corresponding equal to those two sides and the angle that is included between those two sides in the right angle EDC. And therefore those two right angles can go into each other according to side angle side rule. And from the fact that that the right angle CDE can went to the right angle EAM according to side angle side rule. And from the fact that those two right angles can go into each other, we will derive that they have also the same areas. That is to say, we derive that the area of the right angle ECD is equal to the area of this right angle EAM. The areas of those two right angles are equal to each other because of the fact that they can go into each other. Okay, so if we define the area of this triangle EDC as Z, that is to say the area of this triangle M is equal to Z exponents in size, then the area of this triangle ECM, the area of this triangle EAM must be also equal to Z exponents in its size. Again, the area of triangle EAM equals to Z, and therefore the area of the triangle ECD must be also equal to Z. And from the fact that those two right green triangles can go into each other, we will derive that side ED is equal to side EM. Okay, side ED equals to side EM. side EC. Side EC equals to side EM. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles congruent to each other, and therefore those two corresponding sides, that is to say EC and EM, must be also equal to each other in their lengths. In the next step, I copy the right triangle and triangle EMB and this triangle ECD in a new page, and we prove that those two right triangles congruent to each other according to side rule. Okay, those are the two triangles that I proved from the original drawing. So why those two right triangles congruent to each other? First of all, those two sides are equal to each other. That is to say, side EM of this triangle EMB is equal to side EC of this triangle EBC. In addition, those two sides are both equal to 1 and therefore they are equal to each other. That is to say, MB equals to BC. And finally, EB is a common side that belongs to both triangles. So we can see here that EB is a common side that belongs to both triangles. So we can write down that EB equals to itself. It's a common side that belongs to both triangles. So to prove that all the figures of this triangle EBM correspond equal to all the figures of this triangle ECB, and therefore those two right triangles can go into each other according to side rule. And again, the triangle EBC can go into triangle EBM according to side rule. And from the fact that those two triangles can go into each other, we derive that they are also the same areas. That is to say, the area of triangle EBM is equal to the area of triangle EBC. Any two triangles that can go into each other, they must have also the same areas. Okay, so in the next step, we calculated the area of this triangle EBM. The area of this triangle EBM will be equal to the base MB times the height AE over 2. Again, the area of right triangle EBM total equals to the base MB times the height AE over 2. Okay, what is the length of MB? We already found out that MB equals to 1 unit in its length. This is side MB, that equals to 1 unit in its length. So the area of triangle EBM equals to the base MB times the height AE over 2. And again, the area of triangle EBM equals to the base MB times the height AE over 2. MB is 1 times AE. The height AE is also 1. So it is 1 times 1 over 2. 1 times 1 is 1, and 1 over 2 is 1/2. So in total, we found out that the area of this triangle EBM is equal to 1/2 square units in its size. Which again, the area of triangle EBM equals to 1/2 square units in its size. And we already found out that the area of triangle EBM equals to the area of triangle EBC. And from this equation, we derive that the area of triangle EBC must be also equal to 1/2 square units in its size. This is triangle EBC. The area of this triangle EBC must be also equal to 1/2 square units in its size because of the fact that it congruents to this triangle EBM, and the area of this triangle EBM is 1/2. So in total, the area of this the area of those two triangles, that is to say the area of triangle EBM plus the area of this triangle EBC, will be equal to 1/2 plus 1/2. Again, the area of triangle EBM plus the area of triangle EBC equals to 1/2 plus 1/2, that is 1. So in total, the area of this big quadrangle will be equal to 1/2 plus 1/2, that is 1. And again, in total, the area of this big quadrangle EMBC will be equal to 1/2 plus 1/2, that is 1. And again, the area of the big quadrangle EMBC will be equal to the area of triangle BEM, that is 1/2, plus the area of triangle EBC, that is also 1/2. 1/2 plus 1/2 is 1. So in total, if you know that the area of this quadrangle EMBC is equal to 1 square unit size. Repeat again, the area of quadrangle EMBC is equal to 1 square unit size. But what is the area of this quadrangle EMBC? The area of quadrangle EMBC will be equal to the area of the green triangle EAM plus the area of this quadrangle EABC. And again, the area of the big quadrangle EMBC will be equal to the area of this right triangle EAM plus the area of this quadrangle EABC. Again, the area of the big quadrangle EMBC will be equal to the area of the green right triangle EAM plus the area of quadrangle EABC. But we already found out that the area of this right green triangle EAM is equal to Z square unit size. So we can substitute the area of the green right triangle EAM by Z plus the area of quadrangle EABC. And we already found out that the area of the big quadrangle EMBC equals to 1. So the area of this big quadrangle EMBC will be equal to 1. And from this equation, we know that the area of triangle EAM plus the area of quadrangle EABC will be equal to 1. Those two sides are equal to each other. So the area of triangle EAM is equal to Z, according to our definition, Z square unit size, plus the area of quadrangle EABC equals to 1. Why? Because we only found out that the area of the big quadrangle EMBC is equal to 1. The area of the big quadrangle EMBC equals to 1. And the big quadrangle EMBC consists of two shapes. One shape is the green triangle EAM, and the second shape is quadrangle EMCB. So in total, the sum of the areas of those two shapes will be equal to 1. That is to say, the area of the green triangle EAM plus the area of quadrangle EABC equals to 1. So in total, we found out that Z plus the area of quadrangle EABC equals to 1. Z plus the area of this quadrangle EABC equals to 1. Our task is to find out the area of this pentagon ABCDE. So what is the area of pentagon ABCDE? The area of this pentagon ABCDE will be equal to the area of this green right triangle EDC plus the area of this quadrangle around EABC. Repeat again, the area of the big pentagon ABCDE will be equal to the area of the green right triangle EDC plus the area of this quadrangle around EABC. And again, the area of pentagon ABCD will be equal to the area of the green right triangle EDC plus the area of quadrangle EABC. We already found out that the area of this green right triangle EDC is equal to Z. So we substitute the area of the right green triangle EDC by Z plus the area of quadrangle EABC. But we already found out that Z plus the area of triangle of quadrangle EABC equals to 1 here. We already found out that Z plus the area of quadrangle EABC equals to 1. So can I tell that Z plus the area of quadrangle EABC equals to 1. And for this long equation, we derive that in total the area of pentagon ABCD is equal to 1. The area of pentagon ABCDE is equal to 1. Okay. Now pentagon ABCD is equal to 1. Okay. Again, if we found out that the area of this pentagon ABCDE is equal to 1 square in size. Okay, thank you very much.